Hello, my name is Sami, a student in the Advanced Energy Solutions Master's program. I will present to you my master's thesis titled Energy Saving Potential in Outdoor Digital Billboards in Smart Cities. Before I start, I want to thank my supervisor and advisor Paulo and Pramod for helping me with the thesis. Outdoor digital billboards are a common sight in today's smart cities. The problem is that these billboards are usually turned on 24 hours a day. This brings up questions about their energy saving potential. Can there be anything done about this to save some electricity? The objectives of my thesis are to optimize the operation of the digital billboard by minimizing the electricity cost while at the same time maximizing the exposure of the billboard to traffic. We want to find out at which hours of day the billboards should be turned on or off. If we split the day into 24 equal sections that are set to either on or off, there are 16,777,216 different combinations of when the billboard is turned on or off. And hopefully we can find some solutions and strategy recommendations that could be helpful for a decision maker to base a decision on. Because choosing from the initial number of options, it is very difficult task to do. The intention of this work is to find a good balance in the optimization between the objectives and make the recommendations to a decision maker as good as possible. As the data for this project, historical traffic data and historical price of electricity data is used. The traffic data is obtained from Digitraffic and it spans over 10 years. The traffic data used is collected from a traffic measurement system found on Vihdintie because it is located close to an outdoor digital billboard on the same road, about 1.7 kilometers away. This way, the exposure of traffic to the billboard is as accurate as possible. The price of electricity data is obtained from sähkö.tk and it spans over 12 months. The price data is the historic spot prices determined by Nord Pool. Multi-objective optimization is an area of optimization where multiple conflicting objectives are simultaneously optimized. This applies to our case because by trying to reduce the electricity cost by turning off a digital billboard, we also reduce the exposure to traffic. So this means that we can't improve one objective without making the other worse off. These kinds of solutions are called Pareto optimal solutions, and a set of these solutions form a so-called Pareto front or Pareto frontier. To find this Pareto front, we use a simple Python code that iterates through all the possible combinations and finds all the Pareto optimal strategies. Again, meaning that there are no other strategies that offer better exposure to traffic for the same or lower cost, or alternatively the same exposure for a lower cost. In the figure you can see the Pareto efficient strategies as orange dots and a sample of random strategies as blue dots. By finding the Pareto efficient strategies, we reduced the number of strategies to 189 from the previous that was over 16 million. So now we have filtered out all the at least theoretically suboptimal strategies. Now the question is, can the number of strategies be reduced even further? And why would we want to do that? In the figure on the left, we can see that there are still illogical, unbalanced strategies left. For instance, in the lower left corner, there is a strategy that has the billboard off at all times. And in the upper right corner, there is a strategy that has the billboard on at all times. So what can we do to eliminate these? We conduct a threshold-based robustness analysis. And what does this mean? Well, this means that we use a threshold value to filter out the most extreme strategies from the set of strategies. As an example, you can see the figure to the right that represents the frequency of the billboard turned on in all the efficient strategies. If we use the threshold of 0.1, we would remove all the strategies that had the billboard on between 1 and 3, because the frequency of the billboard turned on is below 0.1 at these times. This threshold also eliminates all the strategies that doesn't have the billboard turned on between 15 and 17, as these are also a part of the 0.1 threshold. We use 3 different threshold levels to get a wider range of options. Using a threshold level of 0.1, we eliminate the least robust strategies. As you can see in the figure, the green dots are the efficient strategies constrained by robustness. The orange dots are now the strategies that were removed. And this leaves us with 146 strategies left. Using a threshold of 0.2, we eliminate even more strategies. With this threshold, we are left with 99 efficient strategies. Using a threshold of 0.3, we eliminate even more strategies, leaving us with 44 efficient strategies left. Now we can give a decision maker some good recommendations when to keep the billboard on. The 3 different results based on different robustness thresholds give a variation in flexibility. The 0.1 threshold leaves most room for flexibility, and depending on the preferences of the decision maker, this could be a good thing. The 0.3 threshold leaves least room for flexibility, and again, depending on the preferences of the decision maker, this could be a preferred option. Based on the results, it is always a strong recommendation to have the billboard turned on between 15 and 17 and turned off between 1 and 3. Using the least flexible option as recommendation, the strong recommendation would be to have the billboard turned on between 7th and 8th and between 13th and 18th. Also, the billboard should definitely be turned off between 20 and 4. The set goal was achieved by utilizing multi-objective optimization and robustness analysis. This way, we reduced the amount of strategies from over 16 million to 44. And now we have some solid recommendations to give a decision maker to improve on the energy saving potential of outdoor digital billboards. Thank you.